Warning, the following video contains major spoilers for OneShot, including its Solstice path. It is recommended that you play the game or watch a playthrough of it first before watching this. Thank you. OneShot is a top-down surreal puzzle adventure game developed by Future Cat. You control Niko, a young, cat-looking person who is unwillingly transported into a dying world with no sun. The main aspect of this game is that you, the player, and Niko work together to fulfill the game's prophecy, which is to save this dying, sunless world by restoring its sun. On your way through the game, you help Niko out by completing and solving puzzles, some of which are mind-bending, fourth-wall-breaking puzzles, which use your computer's desktop and operating system as its playfield. OneShot's fourth-wall breaks aren't limited to its puzzles or its narrative, however. Wait, how did Niko get out of it? To say the very least, this game does some of the most mind-bending things I have ever seen in pretty much any video game. This game breaks the fourth wall so much that it might as well not even exist at this point. Looking at all these things that the game does, from finding codes and hidden documents on your computer, to dragging the game off-screen to reveal a code, all the way up to using two separate programs to navigate the endgame. You might be wondering, what kind of black magic does OneShot do that allows it to perform all of this? That is the question that I want to answer in this video. In my quest, I will dive deep into the game's code and unravel how these fourth-wall breaks in OneShot work. Without further ado, let's dive in. OneShot was created and developed in the RPGmaker game engine, more specifically RPGmaker XP, a version of RPGmaker released all the way back in 2005. RPGmaker is a 2D game engine that, well, given the name, provides many of the systems, tools, and assets required to create RPG games. Many popular and niche indie games were made in RPGmaker, with some notable ones including Yume Nikki, Off, To the Moon, and Amori. In order to get access to OneShot's code, I utilized the modding guide created by TehAwesomestKitteh. Using a free trial of RPGmaker XP, along with the mod template created by JokieW, I was able to open up a copy of OneShot in RPGmaker XP, which allows me to access all of the game's rooms, events, scripts, dialogue, and more. This is a good start, but unfortunately, the setup that I have right now is not going to cut it if I want to actually do a full analysis of OneShot's code. As it turns out, spoiler alert, a lot of OneShot's mechanics were not coded in RPGmaker, but instead were coded externally, and many of the game's scripts within the RPGmaker engine simply call that external code. That means that a lot of the code for these fourth-wall breaking mechanics are embedded within the executable file itself, meaning that with my current setup, I cannot see and analyze that code. Thankfully, after some searching around, I found a community re-implementation of OneShot that contains all of this external code. Since this is a re-implementation of the game, there may be some differences between this code and the code from the actual game, as well as some code differences between operating systems. But for the most part, the overall idea should be the same. With pretty much everything I could ever want in my hands, we can now analyze the code behind OneShot. Before I get to explaining the code behind each of the individual fourth-wall breaks of OneShot, I should start with a high-level explanation of some important aspects of RPGmaker and how the game works at a high level. A very important aspect of RPGmaker is that most of its game functions, including cutscenes and interactions, are handled and performed using events. These events can occur when the player either interacts with an object, enters a specific room, or when a certain condition is met, like if the player has a specific item in their inventory. There are two types of events in RPGmaker. First, we have tile events, which are placed within a specific tile in a room, and can trigger actions when the player is in that room or interacts with that tile. Second, we have common events, which are events that can be called or run from anywhere in the game. These events consist of a list of actions that are run one by one when it is triggered. These actions can consist of changing specific game variables, moving the player, showing dialogue, showing a picture, playing sounds or music, calling functions within scripts, and much more. The one we are most interested in are function calls to the game's scripts, which is how the game can run code from an event. Scripts in RPGmaker are written using Ruby, an interpreted, object-oriented programming language that is basically Python, but with more of an emphasis on splitting code and data into classes, a fundamental feature of object-oriented programming languages. Now unfortunately, these scripts in RPGmaker are quite limited in terms of what they can do, especially when it comes to interacting with stuff outside of the engine, and you can see how that would be a problem if you want to implement mechanics that break the bounds of the game, as is the case for OneShot. So instead, OneShot uses what is known as MKXP, a fully open source implementation of the Ruby Game Scripting System, or RGSS, interface used in RPGmaker. Basically, what MKXP does is that it gives the developer the ability to write code for their game in another, more capable programming language like C++, for example, and to allow for RPGmaker scripts to communicate with and run that code. This is accomplished through the use of bindings, which is what provides the interface between the Ruby scripts in RPGmaker and this external code. For the use of this powerful interface, the limitations of the scripting language in RPGmaker are practically lifted, and now, OneShot can perform code that can break the fourth wall. Now that we have an understanding on the overall structure of OneShot's code, it is finally time to analyze these fourth wall breaks. Through my analysis of the game, I have identified a total of 7 different unique and significant game mechanics that OneShot uses as part of its meta aspects. For each of these 7 mechanics, I will analyze how each of these mechanics work by analyzing the code behind it and how it is triggered from the game. These first 4 mechanics are going to be fairly straightforward to explain, while these last 3 are going to be a lot more involved. So, let's begin with Mechanic 1. When you interact with this computer in the first room of the game, the entity, as it is known, explains various things relating to the world and your mission using in-game messages on the computer's desktop. However, its last message, where it says that you only have one shot, shows up as a system message on your computer, unlike its previous messages, giving you its first taste of its ability to break the fourth wall. These system messages are used a lot throughout the game, especially in scenes where important information is conveyed to the player. So, how does OneShot display these system messages? Looking for the list of actions that are within the event that happens when you interact with this computer, there is a call to the edText script, specifically its info function, that has a specified dialogue in it. Looking into this edText script, this info function calls another function, which is down here. In this function, the input text is localized, then it calls a function in this OneShot class, sending it the message type and the text that was passed in. Now, this OneShot class is one of those classes that exists outside of RPGmaker, so we need to look at the reimplementation to see its code. First, we end up in this binding function, which after some string manipulation, calls another function in the OneShot class, which is this function right here. Now the code in this function looks insanely intimidating, but I'll try to explain it the best that I can. The first thing that OneShot does when displaying a system message is to create the buttons that will be displayed on the message box shown here. Then, it sets up the data for that system message in a data object, setting the title, text, and type accordingly. And lastly, using the data and the buttons created earlier, it creates a system message and shows it to the screen. When the user selects a certain button on that message box, it will return true or false depending on what button was pressed. So that concludes my explanation on how system messages are shown in OneShot. Time for mechanic number 2. One of the main aspects of OneShot's meta-narrative is that the player themselves play a part within its story, not projecting onto some other character in the game like a lot of games do, but directly as part of the narrative. One of the ways OneShot accomplishes this is by using your name directly in many lines of dialogue, and sometimes with those system messages that I showed before. How does OneShot get the name of the player exactly? That is what I'll explain now. There are 3 different methods that OneShot can use to get the player's name. The first one is for the use of the Steam API. A lot of games, especially Steam games, utilize the Steam API as part of their operations. This allows Steam games to interact with many parts of Steam, allowing them to perform things like awarding achievements for certain actions, allowing people to invite Steam friends into their game lobbies, and of course, getting user information like their name. OneShot, like a lot of Steam games, does utilize the Steam API. This is how the game can reward Steam achievements as shown here, but it is also what it uses to get the player's name. When the Steam API is initially binded to RPGmaker, RPGmaker's internal username is set to the Steam name of the user shown here. For versions of OneShot that are not on Steam, or if the Steam API is unavailable for some reason, it falls back to method 2, where instead, it fetches the name of the user from the operating system shown here. If the player does not like the name that the game fetched from either the Steam API or the operating system, the game will resort to method 3, where it just prompts the user to enter their name here. Lastly, whenever the game wants to use your name in a line of dialogue, a \p is used, which RPGmaker will automatically substitute for the player's name. And for system messages, the \p is substituted for the player's name before the line gets sent to the OneShot class. So, that is it for mechanic number 2. Now it's time for mechanic 3. Some puzzles in OneShot require the player to either look into or manipulate files in order to solve them. There are 5 different parts of the game that utilize files in some way. 1. In order to get the gas mask required to progress to the northern side of the Barrens, we need to unlock a safe, whose code is included within a text file in the Documents folder. 2. If you want to progress to the final part of the game, you need to open a program in the Documents folder to start that part of the game. 3. If you want to break the one-shot restriction, that is, only being able to play the game once, you need to read a set of instructions in the Documents folder to delete a fake save file. 4. In order to start the Solstice path, you need to enter a password that exists within a set of pages that were written to the Documents path. And finally, in order to access the final area in the Solstice path, the World Machine, you need to move some files from one folder to another in order to unlock this door. So as you can tell, file reading and manipulation is a very commonly used fourth wall breaking mechanic in OneShot. So let's look into how OneShot deals with these files. To get the Documents path, which is what all 5 of these use, the OneShot class fetches the path to the Documents folder, either from an environment variable, a set of common values stored in the operating system, or for a directory lookup if on Linux. Now that we have the path to the Documents folder, let's determine how each of these 5 parts of the game manipulate these files, starting with the safe document. Within the game files, there exists a text file that contains the contents that are part of the text for the document, minus the safe code. One of the first things that the game does when you interact with the computer in the outpost is to generate a random number between 100,000 and 999,999. Next up, it calls a function in the safe puzzle script. It first fetches the path to that text file that I mentioned before, and reads the text from that file. Then, it writes a new text file that contains the original text, plus the random number that was generated to the Documents path. The same procedure happens with 2, 3, and 4, where files that exist within the game's files are copied to the Documents path. For the last one, file management here is a little more involved. When you enter the Vault Room and Cedric, Rue, and Proto are in your party, the game creates 4 folders in the Documents folder, 3 for the small portals and 1 for the big portal. When Cedric, Rue, and Proto go into their respective portals, it copies their respective sprites from the game directory into their respective folders, as well as a text file containing some text. To check where the keys are in each of these portals, there's an event that loops constantly in the Vault Room that calls a set of functions. To check to see if the specified keys exist within the big portal folder, which is done in this function here, it checks to see if the specified file exists in that folder. There's another function that does the same thing, but also checks the small portals. Going back to this event, when it detects that all 3 keys are in the big portal, that's when it determines that the puzzle has been solved and opens the door. The game also uses similar checks to check if the fake save file exists when determining whether or not it should lift the one-shot restriction when the player completes their first playthrough. And with that concludes my explanation on how OneShot makes the player play with files on their computer. Now it's time for Mechanic 4. One of the main objectives throughout the Glen is to save Alula, who is stuck in a room locked off by some glitchy squares. In order to remove these squares, you need to solve a light-up puzzle outside of the room. The solution to this puzzle is obtained from a computer elsewhere in the ruins, which when interacted with changes the user's desktop wallpaper to the puzzle solution which the player needs to use to solve this puzzle. The wallpaper also changes just before entering the final section of the game, turning into a guide for how to open the journal program needed for the final section of the game, which is something I will look into later. So anyways, how does OneShot change your wallpaper? When looking at the event for both cases, there's a call to the setPersistent function in the Wallpaper class, which is a companion class that exists within the OneShot script. All that this function does is just get the file path of the wallpaper of the correct language. Then it calls this wallpaper.set function here, passing in the path name and the color. Going into the binding function, we are met with perhaps one of the longest functions in the entire game, spanning nearly 200 lines of code. A lot of that is just the same procedures but for different operating systems, and even for different Linux distributions, so there's going to be a lot of simplification here. For the code that runs on Windows, the first thing that it does is to get the file path of the image to display as a wallpaper from the game files, just like what it does for the third mechanic. Then, it modifies a few values in the operating system's registry, including the wallpaper style and whether or not to tile the wallpaper, which are just set to 0 in this case, the default values. The registry is a place in the operating system where both the operating system itself and other programs can store values and read them later. The registry happens to be the location where the settings related to the desktop wallpaper are stored. After that, this function is called, which sets both the desktop wallpaper and color registry values in Windows using the passed-in image path and color respectively. And just like that, the desktop wallpaper has been changed. For other operating systems, it mostly does the same procedure, where it modifies the settings within the operating system that are responsible for changing the wallpaper. Alright, so that concludes the first 4 of the 7 fourfold breaking mechanics of OneShot. All of those were fairly easy to explain, which leaves us with the final 3, all of which are going to be a lot more involved in their explanations. Fasten your seatbelts, we are going to be diving even deeper into OneShot's code to uncover how some of these mechanics work. Let's move on to Mechanic 5. In order to get to the surface of the refuge, you need to fix an elevator whose ground button is broken. Once you get the parts required to get the elevator to work, you need to enter a specific code in order for that elevator to open. You get this code from this weird film, which you get by interacting with the computer in the room with the vault door. In order to reveal the code hidden within this weird film, you need to drag the game window outside of your screen and bring it back, and only then will the code be revealed to you. Let's examine how this works. The functionality of the weird film exists within the OneShot class itself. This class contains a map of pixel values, which are saved within this obscured map vector. This map stores a bunch of alpha values, one for each pixel in the game window. These alpha values represent how transparent each of the film's pixels are in the game's window. An alpha value of 0 means that the pixel is completely transparent and invisible, and an alpha value of 255 means that the pixel is completely opaque and visible. When a weird film is opened in-game, all of these values in this map are set to 255, meaning that all of the pixels in the top part of the film obscuring the bottom part is completely visible. Every time the game detects that the position of the window has changed, it performs the code within this update function. The first thing the code does is that it first creates a vector consisting of several Boolean values, one for each pixel of the game window. Booleans are simply values that can be true or false. I'll represent true as a pixel being on and false as a pixel being off. When this vector is first created, all of these values are turned on. We will call this vector the obscured frame vector. Next up, the game creates a rectangle that represents the bounds of the game window, which stores information about where that window is positioned within your desktop, along with the height and width of that window. The game then creates a rectangle that represents the bounds of your monitor, and its position and dimensions within your entire desktop, which itself is a rectangle that encapsulates all of your computer's monitors. Now we have 2 rectangles, one for the game window and one for the screen. Let's move the game window down here, and then we'll also add a second screen to the right of this first screen. You'll see why later. Let's continue forward. The next step that this code does is to try to find the rectangle that represents the intersection points between both the game window's rectangle and the screen's rectangle in desktop space. The code then translates this rectangle from desktop space to window space by subtracting the window's position from this intersection rectangle's position. So now we have a rectangle within the space of the game window that represents the area that was visible on this screen. Going back to that obscured frame vector, we then turn off every value in the obscured frame vector that was within the bounds of this intersection rectangle. Now we do the same steps, but with the second screen. We get the rectangle representing this screen's bounds within desktop space. We find the rectangle that represents the intersection between this screen and the game window. We translate this rectangle's position from desktop space to window space. Then, we turn off all the values within the bounds of this intersection rectangle in the obscured frame vector. This step is repeated for the rest of your monitors. Once the game loops for the rest of your monitors, we are left with a map of Boolean values that show which pixels were off-screen during that specific frame. We then use this map to update the obscured map. We loop over every value in the obscured frame vector, and if any value in the obscured frame vector is turned on, we make the pixel in the obscured map transparent. Lastly, for the use of a shader, the game then sets all of the alpha values of the top part of the weird film to the values that are in the obscured map. And with that, we have just went over how the game reveals part of the film underneath each frame. Now, we repeat this step on every frame that the game window has moved. This keeps repeating until all of the alpha values in the obscured map are set to 0, and at that point, that's when the game determines that the player has fully revealed the bottom film and revealed the code underneath. And with that, we have fully uncovered how the weird film works. Nothing short of absolutely fascinating. In order to progress to the final section of a pre-solstice run of OneShot, you need to open up a separate journal program in order to start it. Throughout this final section, you need to use this program in order to reveal and find the correct pathways and solutions required by hovering it over the game's window. This is probably one of the most technically fascinating aspects of this game. Using 2 different programs as part of its fourfold breaking mechanics, it's crazy. Looking at the code for how all of this works, you can definitely tell that there was a lot going on here to accomplish this mechanic. Since the code for this mechanic is so insanely long and complicated, it would be best to just stick to a high-level understanding of it, so I will be oversimplifying a lot here. The basic premise of this mechanic is that the game is trying to communicate with a separate program on the user's operating system, using some form of inter-process communication. Inter-process communication is a mechanism that allows 2 or more separate programs to effectively communicate with and cooperate with each other to accomplish a common goal. There are 2 different ways that inter-process communication can be done. One mechanism that can be implemented to accomplish inter-process communication is by allowing both programs to share an area of memory with each other, which is often called the shared memory model. The other mechanism of inter-process communication involves the 2 programs sending and receiving messages to each other using some kind of a hardware bus or through a network, the latter being the most common form. This mechanism is often referred to as the message passing model of inter-process communication. OneShot uses the shared memory model of inter-process communication to accomplish its interactions with the journal program, using what are known as pipes. When a program opens a pipe, it initializes a field of memory in the computer's operating system that both it and other programs can read or write from. When the player first opens the journal program, it first initializes a half-duplex or one-way pipe that the game can write to and that the journal program itself can read from. Every time the player switches rooms in the game calls this journal set function, which sends a string consisting of the name of the journal page appropriate for the room that the player is in through the pipe that the journal program created. When the journal program reads this string from the pipe, it loads the specified image from the game's directory and displays it inside of its window. This procedure happens every time the player switches rooms. When the player finishes this ending sequence, the game sends an empty string for the pipe, which the journal program responds by closing itself. So there you have it. That is how OneShot and the journal program communicate with each other. Now let's move on to the final mechanic. Last but not least, we have probably the most fascinating fourfold break of the whole game. If you select Return Home during the final choice of the game, you get this scene where Niko thanks you for sending them home. After this, Niko does the unthinkable and walks outside of the game window down for your desktop, literally breaking the bounds of the game. The same thing also happens if you successfully complete the Solstice path, where Niko walks out of the game window towards their home, but this time with the world saved as well. Now the question is, what kind of black magic does OneShot perform here to allow for Niko to literally break the bounds of the game? In the events where this fourth wall break happens, it calls this function in the Niko class called Do Your Thing. If you didn't already guess, this is the function where Niko, does the thing. So well, how does Niko do the thing? Going into the binding function for this method, we are met with the following code. The first thing that it does is to get the current position of the game's window. Then it uses the position of the game window to get the screen position of where Niko is currently standing using a hard-coded value in the binding class. So far, so easy. But now, get this. The game then gets the path for the journal program and runs it, passing in the position of Niko as arguments. Wait a minute, why are we executing the journal program exactly? Well, as it turns out, the journal program actually has two separate functions. The first one we've already explained, which is to act as well the journal for the final area of the game. However, the second function of the journal program is to act as a separate version of Niko for this final scene, which has the ability to walk outside of the game window and browse your desktop. So now, let's look into what the journal program does when it is first created in this scenario. In the main function, it calls this do Niko function, passing in those positions that were passed in by the game as arguments. In this function, it first fetches Niko's sprites and saves them within this bitmap array. Then we have all of this code, which simply creates a borderless, transparent pop-up window at the specified coordinates that were passed in earlier. It then gets both the total height of the screen as well as the window's rectangle, which will be used for moving it later. Now we get to this infinite loop down here, which is where the magic happens. This first part here dispatches a message that runs a function that handles drawing and animating Niko's sprite within the window. After the sprite is drawn to the screen, the window's position is then moved down by 2 pixels. This is then repeated 60 times per second, where we update the sprite within the window and move it down by 2 pixels. This repeats continuously until the top of the window goes below the bottom of the screen rectangle. When Niko goes below the bottom of the screen, the journal program closes. Niko has finally made it home to Mama. The credits roll within the game screen, and moments later, the game ends. And with that, that is how Niko can break the fourth wall in this final scene of OneShot. And there you have it. That is all 7 of OneShot's fourth wall breaks explained. At least all of the significant ones. Now there are a few other fourth wall breaks that OneShot uses beyond these. These include the dream sequences, closing the program while on the tower, and the one-shot restriction. The code for those mechanics is fairly trivial, using a combination of safe data manipulation and closing the game. But other than that, that is everything I wanted to know about OneShot's fourth wall breaks. So hopefully from my journey for this rather technical deep dive of OneShot's code, you now know that OneShot did not perform any black magic to accomplish its fourth wall breaks. It was just for the use of some clever code. Now before I go, I would like to give a huge thanks to a lot of people in the OneShot community for providing all of the required resources for me to make this video, and for providing details whenever they were needed. Huge thanks to TehAwesomestKitteh and JokieW for providing the guides and tools needed to help me access the game's files, and to all of the contributors behind the MKXP-OneShot repo for providing the re-implementation of OneShot's code, which I referenced throughout this entire video. Trust me, without all of these things at my disposal, this video would have not been possible to make at all. So on that note, I am Red, and thank you for watching.
you.